Our next awardee for science and presenter is Dr. Karl Gebhardt. He is Herman and Joan Suit Professor of Astrophysics in the Department of Astronomy at the University of Texas in Austin. He grew up in Rochester, New York, as he calls it, and I'm familiar with it, and I've been there and have suffered through it, a snow-filled cold country. Got his Ph.D. from Rutgers. He came to UT Austin in 2003 through Michigan State and University of California at Santa Cruz. He's also recipient, like Dr. Deem, of NSF Career Award, and I'm going to let him tell us about his work. While he's coming here, I'm going to tell just one tidbit that I read in it. He has measured more black hole mass than anyone else in the world, definitely more than I have.
So thank you very much. It's a real pleasure to be here. It's a real pleasure to talk to you today, and I am extremely honored to have this award for this year. So I spoke to this group maybe 4 or 5 years ago. I talked on dark energy. I know that there's been a lot of topics, a lot of discussion on energy the past 2 days. I'll give you my take on the energy of the universe. So let me tell you about what I'm doing, why we're doing it, and I'll put it in context in terms of the big picture, in terms of astronomy and the universe. So if we go to the slides here, there's a few images I have here, so just for eye candy here. So on the top right is a picture I worked on with a graphic artist on, the view of a galaxy if you were close to a very massive black hole. Okay, and I'm going to talk about that later, so we have some new results on the most massive black holes in the universe. On the top left is the image of what the universe would look like if there were a black hole of about 10 times the mass of the sun at about the distance of the moon. It would look really, really cool for about 10 seconds, and then we'd all die, but it would be a really nice image and view of the universe. And in the bottom image is where, so most of my career so far has been in measuring black hole masses, and I'll talk about the importance of that. The bottom image is where most of my energy is going now, and I'm using the Hubble telescope to understand why our universe is expanding the way it is. This is to try to understand the nature of dark energy. Hubble telescope is a telescope that we own, that the University of Texas owns a substantial fraction of. It's out in West Texas. It's a beautiful spot if you get a chance to go out there. So let me talk about each of these, and let me try to place it in context. So here I have two images. The top image is an image of the universe if you could look in microwaves. So this is the cosmic microwave background. And what I'm showing here is an image of the whole universe. There's a laser pointer here. So we live in a three-dimensional world, and I'm trying to display things on a two-dimensional structure. So how you do is you do these types of projection. So this spot here is the same as that spot there in the universe. That spot there is the same as that spot in the universe. And you wrap this around your head. And so that's how we project our universe onto a two-dimensional structure. The top is an image of the universe when it was 13.5 billion years ago. So it was extremely young. It's the youngest picture we have of the universe. Since the universe has been expanding, so this is very, very small. This is the size of quantum fluctuations is what we are looking at. We are looking at structure that is well inside of a particle. Okay, so this is a baby picture of the universe. The bottom picture is how the universe looks now, where what we've done is we've removed all the pesky stars and we're just looking at galaxies. So each of the points here is a galaxy, and this is how the universe looks now. So our job, what we're doing as astronomers, is we're trying to understand how to go from point A to point B. This is just how the matter and energy was distributed early on in the universe. This is how it is distributed now. And the things we need to tie in to make this, to make a model, is to understand how the universe came into existence in the first place, to understand where the energy and matter came into existence in the universe. And then you want to understand how it comes together to make a large structure, how it makes a galaxy, how you make a star inside that galaxy, how you make a planet around that star. So there was just a huge press release, maybe, I think it was yesterday or 2 days ago. So there's a major meeting in Austin now of the American Astronomical Society, and there was a big press release that there are about 10 times more planets out there than there are stars. And that just means that every star has a planetary system around it. And trying to understand where those planets come back, it feeds all the way back into how you make a star, how you make a galaxy, and how you make structure. So that's what we're trying to do in terms of the big picture. And one of the huge things is to try to explain where we're going to go in the future. Right now, our universe is expanding at an accelerated rate. The 2011 Nobel Prize in Physics went to the discovery of the accelerated expansion. Galaxies at the edge of the observable universe now are moving away from us at a speed substantially faster than the speed of light. Now, I think we all have learned that nothing can go faster than the speed of light. You cannot travel through space faster than the speed of light, but space itself can expand. There's no cosmic speed limit for how fast space can expand. It can expand significantly faster than the speed of light. We are a galaxy on one side of the universe, a galaxy on the other side of the universe. We are going along for the ride. We are going away from each other at faster than the speed of light. That is a very interesting phenomena because it implies that we are not, at some point, we'll never be able to see the galaxies at the edge of the observable universe that we can see now because they're expanding away from us at faster than the speed of light. So, and the expectation, if you take the simplest explanation for what this accelerated expansion is doing, is that in 10 billion, 100 billion years, which is not a short time in terms of astronomy, we will have no galaxies that we can see. So the joke is we have to hurry up as astronomers in order to understand because we won't be able to see any galaxies so relatively soon. Okay, so what we're doing is here are two pictures of theory against observations, and I just want to put everything on scale and tie together the work I'm doing on black holes to the work I'm doing on the expansion of the universe. And so theories on the left is one of the most advanced computer models out there, and the observations are on the right. And what you're looking at here are, each little point here is a galaxy, each little point here is a collection of dark matter. Most of the universe is dark matter. When we talk about matter, it's predominantly a dark matter. There is about 7 to 8 times the amount of dark matter compared to normal matter, where normal matter is the stuff that we are made of. And if you zoomed in to one of the points there, you would see a galaxy. Here's one of my favorite objects. So this is the Sombrero galaxy, for obvious reasons. And if you zoom in even more, you'll see there is a black hole inside this galaxy. You can't see the black hole. All we can see is the material around it. So why does this matter? Because what we're trying to do is, if you want to make a picture for how the universe evolves over time, you need to understand each of these components. And you need to understand how they work. The black hole is attractive. It's a collection of mass, and it wants to pull things in. It has a positive pull of gravity, so that will pull things in. A dark matter is at the edge of a galaxy. I'm not going to talk about what the dark matter is so much. That's an area I work on, but just for lack of time, I'm not going to talk about that so much. But that's attractive as well. That's just the expectation. It's a new type of particle we have yet to discover. And dark energy, though, works on the largest scale. So black hole, it works on very small scales. The dark matter on intermediate scales, and dark energy on the largest scales, and that pushes things apart. This is where the acceleration is coming from. I'll explain that a bit more in a second. Okay, so this is our cosmic pie chart of what's in the universe right now, of what we think is in the universe. How we know this is we try to quantify how the universe is expanding and what are the constituents that causes that expansion. So we measure the expansion rate, and then we see how much matter, how much normal matter, and how much is remaining for dark energy. And here's the pie chart that we have. The majority 74% of the energy in the universe is in this stuff called dark energy. 21% is in this stuff called dark matter. The stuff that we know and love is the remaining 4% or 5%. Okay, so every time I look at this, I'm always kind of blown away. 95% of the universe is in stuff that we don't know anything about. This is the amazing thing. So we're trying to make a model for how the universe came into existence, how you make a galaxy, a star, etc., where the universe is going to go, and we don't understand 95% of the material in the universe, of the energy, of what's causing that expansion. Okay, we think we're getting a handle on dark matter. We think it's a new type of particle. I think within a year or two, I think we're going to have a dark matter detection in a physics experiment. And dark energy is just a complete mystery right now. It is an embarrassment. It was discovered in 1998. To have discovered that we are missing 74% of the energy in the universe in 1998, just over 10 years ago, is a remarkable thing, actually. Okay, so I'll explain more about that. But so here are the best explanations, and then I'll go into a little bit more detail. So a black hole is just an area where the mass is so concentrated that a gravity will win over all other forces, and everything collapses to a point, is what our calculations show now. Okay, and this is where the theory breaks down, because everything collapses to a central, a point of infinite density. We don't like infinities in science, so we say that something is wrong with the theory. It's likely what is going on is it's a new state of matter that we have yet to understand. And people go crazy with, it's a portal to another dimension and and we have no idea. Okay, so dark matter, I'm not going to spend much time on. We know it's been around, the problem's been around for a long time. We're getting close to solving the dark matter. As I said, I think we're going to find the dark matter particle. So within a year or two, there are some suspicions now that we've found the dark matter particle, and that's very exciting. It's just probably a new type of particle that is just, it doesn't interact with matter very well, and so that's why it's hard to detect. So dark energy, as I said, it's only been around for 10 years or so. It has the opposite sign. This is why it's so complicated. It is causing the universe to be pushed apart, and the only consensus that's out there is that we have a problem of what a dark energy is. Okay, and here's where they've struggled in terms of the theory, and it's really it's an observational game now, and I'll talk about what we're trying to do in order to understand that. So let me switch to how we measure all these things. Is how you measure a black hole the same as how you measure a dark matter, is how you measure a dark energy. We don't think that black holes and dark matter and dark energy are related in any physical understanding. But where you use the same techniques to try to find them, because you can't see these things, and so you have to use objects around them in order to try to find them. So how you measure it, here's one of my favorite galaxies. This is M87. It's one of the more massive galaxies in the nearby universe. What you do is you just see, and there's a black hole sitting in the middle here, which we can't see because it's a black hole. And what you do is you just see how fast the objects are moving about it. You just use Newton's law. We just heard about Newton's laws, and now we just see how fast the objects are moving, and that will tell you what the enclosed mass is. And so what you do is you take a spectrum, and you take a spectrum at each point around the galaxy, where you break it up into the individual wavelengths, and then you see what the Doppler shift is. That tells you how fast it's moving, and you make a model, and this will tell you how fast the stars are moving here. If you want to do it for dark matter, you do the same thing. You take a spectrum of all the stars out here, and you see how fast they're moving, and you make a model for how much matter is supposed to be there. And when you do it for dark energy, you want to see how fast these galaxies are moving away from each other. You take a spectrum here, 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 and you see how fast the galaxies are moving. So it's all the same thing. All you're really doing is you're taking spectrum. That's the essence of what we do when we try to measure a black hole and dark energy and dark matter, and you see how fast the objects are moving, and you make a model. Okay, so let's go in a little more detail, and let me a brief history of black holes. Just very, very, very quickly, Black holes, the idea of a black hole has been around since the late 1700s by Michel and Laplace. They came up with this idea, they called it a dark star. How it works is we all understand the idea of an escape velocity. You have to go, you have to reach a certain velocity from a body of a certain mass in order to escape its gravitational pull. Okay, and we all understand that. So at the time, at the late 1700s, they were beginning to understand that the speed of light is finite. There was a debate, so much before that as to whether it's infinite or whether it's finite, but at the time it was realized it was finite. And so if it's finite, you can imagine an object that has so much mass, so concentrated, that light cannot escape. It's just a trivial theoretical game. And that's what Michel and Laplace did, and they called these things a dark star, saying that if it had that much mass, light could not escape. And then it stayed in the theoretical regime for a very long time. Of course, Einstein, he came up with this idea of general relativity. Schwarzschild solved these and showed that inside, so if you put so much mass in such a volume, then the gravitational pull is so strong that nothing can stop it anymore, and all the matter falls to one point, an infinitely small point, and this is what is called a black hole. Okay. Again, I don't think very few people believe that you actually go into an infinitely small point, that we have to adjust our equations of general relativity, and this is what string theory is working on, for example, but we're not there yet. Okay, so it just stayed in the theory game. So whether nature had them or not was not quite highlighted. And then it wasn't until Hubble Space Telescope was launched where we began to measure these black holes. Okay, and this is where I came in the late 80s, and I was starting right when, soon after Hubble Space Telescope had been launched. The advantage of Hubble Space Telescope is that it can see very fine detail. If you want to measure a black hole, it's sitting in the middle of the galaxy, it's very small. You got to get the stars that are really close to the black hole and see how fast they are moving. And when we tried to do this previously from the ground, the blurring of the atmosphere would cause us not to see the fine detail that you can get from Hubble Space Telescope. So it wasn't until Hubble Space Telescope was launched that we can see how this works. And so here are some images of the central regions of some galaxies. They are rather boring, but once you look at the velocity, what you see is that, this is a measure of how fast the stars are moving as a function of radius, and as you get close to the middle, the stars go faster. You make a model, and you need a black hole. One huge revolution in astronomy that's happened in the last 10 years is the advancement of a technique called adaptive optics. Adaptive optics is this fantastic technique where you take the ground-based telescopes and you effectively turn them into a Hubble Space Telescope. And how you do it is, here's your telescope, there's a big mirror here, here's your instrument. You shine a laser off the top of the telescope, a very powerful laser. You shine a laser off the telescope, it hits the upper atmosphere, it bounces back into your instrument, and what you do is you adjust your mirror to make that laser spot that comes back in as small and tight as it possibly can be. And then what you do in that case is you're compensating for the twinkle, twinkle, little star. You're compensating for the atmosphere. It's blurring. And so what you do is you turn these ground-based telescope into these space-based telescope, and it's fantastic. I'm a big user of one of the Gemini telescopes. So this is a National Science Foundation telescope that's in Hawaii and in Chile, and here is some of the data. And so this is the data in the galaxy M87, where you see a large rise of the black holes, of the movement of the stars in the middle of the galaxy. It implies a black hole. Let me explain a bit more how. So here's the actual image of the telescope and the laser. Ignore the background, but this is a real image of the telescope and the laser, and it really is spectacular when you see these things. They've gotten into trouble with the FAA because they have to worry if you hit a plane, it's not going to be good. But they have planes normally aren't flying over telescopes. So let me explain why it's complicated and where I came in to play. What I do is I write computer programs, and that's mainly all I do. And I wrote a very a fancy computer program. I'm an observer mainly, but then I do the data analysis. And why it's so complicated is that there are a lot of stars in a galaxy, and they can move in a variety of ways. They can move like a planet will move about the star in a perfectly circular motion, or they can move like a comet, where they come flying in on a perfectly radial motion. So when I look at when you take an image of a galaxy, it looks like, here's some pictures of galaxies on the bottom here. When I look at a galaxy, I try to visualize it in terms of the stars that are orbiting. Here's one orbit of a star. You can track it as it goes around a galaxy. If you run it for a very long time, for billions of years, it looks like this. If you run it more, then one star will have a footprint like that. Another star will be like this, this, this. When you add all these up, you get a galaxy. So the complication here is trying to cover the phase space that's available for how the stars can move in a galaxy to make a model of the galaxy. And so what we do is I run these very sophisticated computer models where I try to mimic as many stars as are possibly there, and then you match that to your data. Okay, and so, and you have to do this on supercomputers. At Texas, we have one of the biggest in the world. At the University of Texas at Austin, we have a 60,000 node computer that I use all the time. And so that's basically how it works when you measure these things. And so here's the correlation I found some time ago. That is, here's the data. Here's the mass of the black hole on the vertical here. And so this is against, effectively, it's the mass of the galaxy. It's no surprise. What we've found is that the bigger the galaxy, the bigger the black hole. That's no big deal. But what is a big deal is that it's almost a perfect correlation once you take the error bars into account. We never see a perfect correlation almost in anything in science. And what we're finding here is that there's almost an exact one-to-one correlation between the mass of the black hole and the mass of the galaxy. We have newer data where now here's the same plot. Here's the mass of the black hole and effectively the mass of the galaxy. And it's been holding up. I did the correlation back in 2000, and it's holding up now. And what it has to do with, it's a fundamental relationship for how you make the galaxy. What we believe is going on is that as you add mass to the black hole is this tiny spot, and as you try to pile that mass in, you just can't squeeze that amount of material into such a small spot, and it fights back with winds and jets. Those winds and jets interact with the material that's falling in, and it'll blow that material off. So as you feed the black hole is able to regulate the amount of mass you have in the galaxy. This causes that fundamental correlation. We had never thought previously that black holes would have a lot of influence. They were just thought to be a side product of how you make a galaxy, but now it appears that they are actually fundamental. And it's because of this correlation that we found, and there's lots of theories out there, but the theory that is coming to pass is this idea of the feedback. Try to put the mass in the black hole, it fights back. Okay, so that was black holes. Now let me move, so that was what I used to do. What I want to talk about a little bit about and end with is the project we've been working on called HETDEX. I spoke to you folks a few years ago about this, but let me just try to give you an update. So HETDEX is the Hobby Eberly Telescope Dark Energy Experiment. All right, and there's our collaborators here. It's a lot of contributions from our German collaborators, but it's run completely out of Texas. Our idea, we raised 95% of the money, and it's our telescope that we are using. The problem is, as I said before, is that the universe is accelerating. And how we do it is with this very simple equation here. What you do, if you want to measure what's in the universe, you measure how fast the galaxies are moving away from us. This is not a hard measurement. You look at galaxies nearby, we know how far away they are, we know how fast they are moving. That's the expansion rate. So this is the observation over here. So this is what we measure. This is the expansion rate. And then we have to know what's in the universe. There's matter in the universe, and so that's a matter term. And there's no matter and dark matter. Once we try to compare the expansion rate compared to what we know in the universe, we're expanding about 3 times faster than just the matter would allow in the universe. That ignorance of the expansion is what we call the dark energy. So we had to add a term over here. And once we don't understand something, that's what we do. We added a term, and that's the dark energy term. And as we always say, it may not be dark, it may not be energy. It just may be that we don't understand what's going on in the universe, okay? It could be that we don't understand how gravity works. That's that's one explanation for what it may be. It could be that it's a product of space. That's the main idea, that space itself has an energy associated to it. As the universe expands, there's more space, there's more dark energy, and then it gets us to push apart. That's the acceleration. That's one of the ideas as well. Or we just don't understand how gravity works. Or there's a new type of particle. That's called quintessence, the fifth essence. That's a new type of particle, it's a new force that we have yet to understand. Okay, so let me jump through these ideas here. So let me just, I want to get to our experiment because I know I'm running out of time and I just explained these. But what we do in HETDEX itself is what we're trying to do is we're just trying to measure that expansion rate as accurately as we possibly can. And how we do it is we take an image of the universe a long time ago and we see how the galaxies are distributed in the universe. So what we're going to do is we're going to make a very detailed map, the most detailed map ever of the universe. We're going to use about 1 million galaxies, see how they're distributed, and we know from this baby picture that I showed before that they're not distributed perfectly uniformly. There is a pattern for how the galaxies are distributed. And so just like there's a fingerprint for each of us, our universe has a fingerprint for how the matter was distributed. As the universe expands, the fingerprint expands. And so all we're trying to do is we're trying to find that pattern at different times in the universe, see how big that pattern is, and that's the expansion rate. And that goes back to what the dark energy is. So the idea here is just to take as many spectra of galaxies that we can possibly do. And we have an instrument that was actually funded by George and Cynthia Mitchell. So this is one spectrograph. We put it on our small telescope, on a 2.7 meter telescope, and we just, to test out our idea, this was a prototype, and it worked fantastically well. Now we're going to build 150 of these spectrographs and put it on a 10-meter telescope. And so what we did, I had a grad student, he's spent 150 nights at a telescope to take data on this. Once we put this instrument, our new instrument, on our 10-meter telescope, the amount of data he collected in 150 nights will take an hour on the 10-meter telescope. And he's depressed. But he got a really good job, and so he should be okay with that. So we're working on that now, and let me just, the advantage of HETDEX, and I'll place it in context, and I'll end here in a second. Here is a cartoon sketch of how the universe expands, time equal to the beginning of the universe here, time equal now, this is today. And there you can see a tiny hook right here. This is the idea that our universe is accelerating. Here's where the folks got a Nobel Prize at trying to measure this tiny hook here. So all the experiments are focused on what the universe is doing now. So our experiment is going back in time where no one's ever looked for what the universe is expanding. From here to here, so this is a cartoon sketch, our understanding is a cartoon as well, as far as I can tell. So here, the only measurement we have of dark energy is right at now. We're going to look back in time, and once we compare these two, then that's when we get to the understanding of what's going on in the universe. So we're going to start our experiment probably at the end of this year. We'll start taking data at the full strength probably in January or February of next year, and we'll go for 3 years. It's a very powerful experiment. It's unique. It just came from the American Astronomical Society meeting. So all the competition is gone. We have all our money, and I hope maybe in 4 or 5 years to come back and tell you what the expansion is. So thank you, and thank you for the award very much.
Rustam Modi with Baker Hughes. I just feel like I just got off a roller coaster. I mean, this thing just blew me away.
Say that again.
I just feel like I just got off a roller coaster.
Okay.
Okay? 2 questions. The baby picture of the universe, when was that taken?
When was the baby picture? So that was a picture taken by, it's the Wilkinson microwave anisotropy probe. It's the WMAP satellite that came out about maybe 5 years ago or so. There's been many microwave pictures, but that's the best. So that was taken between 5 and 10 years ago in total. But that picture is when the universe was about 400,000 years old.
Okay. So within the next 3 or 4 years, you're already out to the outside limits now, looking at the pictures?
So there's no, so okay, so that's, we can't, there's no more information that we can get except for that picture. That's the best that we can get. That's not going to improve. I mean, there are going to be slight improvements in terms of trying to see a detail, but it won't evolve. In astronomy, nothing evolves.
Okay.
We don't see anything move. We just, it's a snapshot, so the experiment's been done, and that's what we have to go with. So in a few years, we'll take a picture of the universe as it existed about 10 billion years ago. That picture was a picture of 13.5 billion years, and once we compare those two, that's where we get our leverage of how the universe expands over time.
And the other concept I have trouble understanding is when you talk about a universe expanding into what?
Okay, fine, good. So you're right. So, okay, I shouldn't have said the universe is expanding. That's what everyone says, and it leads to exactly that confusion. The proper way to put it is that the average space between the galaxies is increasing. We're not expanding into anything. The space itself is defined essentially by where the matter and energy is. And so there, a common question is, what's beyond our universe? Well, it's not defined according to our math in terms of the universe that we live in. That doesn't mean you can't theorize about some other type of dimension, but you're not allowed to ask the question what's beyond our universe because it's not a definable property. It's like saying, what's the center of our universe? There is no center of our universe. That means there is no edge of the universe.
So basically what you're saying is that galaxies are rearranging within a fixed space?
No. Let me give the analogy. So maybe this will help. So if we were creatures who could only live on the surface of the Earth, okay? And we can't imagine flying planes or digging tunnels. And so we are creatures that live on the surface of the Earth. And I ask you, what's the center of the surface of the Earth? Maybe some will say Texas, but there is no center to the surface of the Earth. And if the Earth expanded, if the Earth began to expand, and we were creatures who lived on the surface of the Earth and did not know about that, we would just see, so you and I would begin to go farther apart. We would say, oh, my distance is increasing. So that's because, and why it's hard to envision that is because we understand the idea of 3 dimensions. But if we were 2-dimensional structures, then we would see that expansion and we would say, oh, my average distance is increasing. And so when we talk about the expansion of the universe, you can imagine that there is a higher dimension out there that we can't visualize. It's completely analogous. So if you can appreciate that there's no center to the surface of the Earth, then there is no center to the universe. And if there is no center to the universe, there's no edge to the universe either. Did you get that?
I'll take your word. I'll take your word for it.
Thank you.